So today we're working on two things. We're going to do some areas of triangles, and we're going to do some comparing. We've compared on and off throughout the years in a variety of things, and that's coming back to us today. But the first thing we're after is how to do the areas of triangles. Areas of triangles are a little bit similar to areas of other shapes. Okay, if we think through our year, you might remember we've done some things with perimeters of shapes. Perimeter, we go around the shape. We add every time we do a perimeter. Areas is always the space inside the shape. We've always multiplied every time we've done an area, and that still continues to be true. What's different about triangles compared to every other shape we've done, and every other shape pretty much that you'll ever do, triangles, to do their areas, you're going to have to cut things in half, and I'll show you why in a second. But the formula for how to do the area of a triangle is that we're going to multiply the base times the height, and at some point in the problem, whether it's at the beginning or at the end, doesn't really matter, we've got to cut something in half at some point. Okay, so base times height, and we're going to cut in half. How you know the base and the height is always a dotted thing. The base is whatever that is perpendicular to. And if that seems like that's familiar, we did that exact thing with parallelograms. If you remember when we did areas of parallelograms, we'd always look at the shape and scan for some kind of dotted line. And we always use the dotted line. Triangle, similarly, we're always going to use the dotted line. Then we look for whatever the dotted line is perpendicular to. Perpendicular meaning it makes a right angle, like a perfect T, whether it's right side up or upside down, or like a perfect L. You know, nothing going diagonal, but like a right angle L or T kind of a thing. So on this shape, we definitely want to use the 2. The 2 is the height, that's the dotted thing, scan for that, that's the easiest thing to find. So we're going to use the 2 for short. And then you try to decide who is the 2 perpendicular to. Since the 2 goes straight up and down, we need a friend that goes straight across, whether that's a T, or like an upside down T, or an L, or whatever that may be. And that number we want to use is the 8. So we're going to have to multiply 2 and 8, and at some point we've got to cut something in half. So you could either go 2 times 8 is 16, cut 16 in half, settle on 8. Or you could cut the 8 in half, it's 4, then multiply, it's still 8. Or you could cut this in half, it's 1, times this, it's still 8. Doesn't matter what order you do the steps. You've got to multiply, and at some point cut something in half. So for this next one, pause the video, think about it. First thing we've got to do is pick which 2 numbers we want. We want this 5. Always use the dotted thing. The dotted thing is always going to get used. And then we figure out what's the dotted thing perpendicular to. The 5 is perpendicular to the 8, so we want to use that number. I'd rather not cut 5 in half because it's odd. It's a little awkward. So either 5 times 8 is 40, and then cut in half to 20, or half the 8 is 4 times 5, still 20. We'll save a word of advice for the end. This one you might be a little freaked out about because you don't see a dotted line. Okay? You don't see a dotted line because 2 of the sides themselves are perpendicular to each other. So either of these, either the 3 or the 4 could act as the way the dotted thing usually acts. Either of those could really be considered the height, I suppose. The 3 and the 4 to each other are already shown to be perpendicular. So we'll want to multiply those 2, and again, cut something in half. So 3 times 4 is 12, cut in half is 6. Or half the 4 is 2, times 3, still 6. We do one small change of shape, just so you don't get a misunderstanding out of this. The dotted thing doesn't always have to go straight up and down. You'd sort of expect that out of the height, that it should go straight up and down, but realize these shapes could just get turned. If I took this shape and turned it, this wouldn't be going straight up and down anymore, but it would still have the same area. Okay, so if somebody wanted to draw your dotted thing this way, to be perpendicular over there, that's totally fine. Okay, so let me say 6, 7, 8, 10, something like that. If I draw the dotted thing going through this way, we still always use the dotted thing. 6 has to get used, and then you figure out what's it perpendicular to. What does this make that T with? And it's with the 10. The 6 and the 10 are the perpendicular sides. 6 times 10 would be 60. Half of that is 30. And on we go. Or we could have done half of 10 is 5. Times 6 is 30. Or half of 6 is 3. Times 10 is 30. All roads lead to 30. Another thing I could do on these, the book does sometimes on these, is they'll put units of measurement on them. So remember, if they decide to do inches, you need to do inches. But for area, we don't do regular inches, we do square inches, which we can show that by putting a little 2. Or if they do meters, you do meters. You don't have to do the little 2. You could just put like an SQ on it. If you'd rather do that, that's fine. If they just do numbers, you just do numbers. Don't put the little 2's or SQ's on something without a system of measurement. Just go with numbers when they go with numbers. But if they decide to do inches, you need to do inches, and then you decide how do you like to show that it's square inches. Area is always square inches. One last thing before we move on. I told you at the beginning I would tell you why we were cutting this in half, I believe. Reason being is this triangle is really half of a parallelogram. If I take this side and I draw a parallel line up top that matches its length, those are about the same length. And then I draw another thing over here where these are the same length. I now have a parallelogram. We did areas of parallelograms back a ways. We wouldn't have had the 4 there. We wouldn't have had that diagonal line there. But we've done areas of parallelograms like this, where we take 2 times 8 is 16. But when I made this into a triangle, that was the original picture there. This is half of that parallelogram. So we're cutting things in half. Likewise for this, if I completed this shape, this is now a rectangle. Okay, I have 3 times 4 is 12. This rectangle would have an area of 12. But now that a triangle's been created instead, and that top was never supposed to be there, we have half of that 12. We have 6. Okay, so triangles, we always cut in half, because they could be made into bigger shapes that we've done before, and the triangle is half of that original shape. Last thing we're doing is comparing. So we've compared before, compared whole numbers, compared fractions, compared decimals, we've compared all kinds of stuff. I don't think we've ever compared with negative numbers involved. So they get around to doing this in a lesson, and we'll do this today and lump this in with the area, because neither of these is like a super complicated concept. Comparing with negatives, you can think of 2 ways. The fail-safe always works thing is think about the number line. And if you can swap numbers on the number line, the bigger numbers are always on the right, and the smaller numbers are always on the left. And that's a way that you could do anything compared and just be sure. If you don't want to look at the number line, another thing you can do is just realize that when you do negative comparisons, it's the opposite of what we were. Just like in English, if you put a negative in a sentence, you made the sentence opposite. When you put negatives in math, you create some oppositeness. Like, I did my homework. If I make a negative in that, I did not do my homework. Okay, the not makes that a negative sentence. I turned that around. It's the complete opposite meaning. Positive 3 compared to positive 2 would always be bigger. 3 beats 2. But when we go into the negative world, negative 2 beats negative 3. So you can think of that either way. If you want to think about how it's the opposite relationship from usual, fine. If you want to check the number line, I'll venture a little bit to my left here and we can point at the number line. Here's negative 2 and here's negative 3. The bigger number is always the one that's on the right. So negative 2 is a winner over negative 3. Or if you don't like either of those, think about like temperatures. Here we are in the winter. The temperature could be negative 2. The temperature could be negative 3. You're not real thrilled about either temperature, but if you had to pick one, you'd pick the negative 2. Or if you're a sports fan, football fan, your team's losing 2 yards. Your team is losing 3 yards. You're pretty mad at your team either way, but if you had to pick one, you'd rather lose 2 yards. Or if you like money, this is you owing your friend $2. This is owing your friend $3. You're not real thrilled either way, but if you had to pick one, you'd rather owe them $2. If you think you got a handle on that, pause the video, take a second, do the rest of these. For this, we're going to go with another greater than sign. The -4 is greater. Usually 5 beats 4, but throwing negatives in has reversed the situation. Alternative thought, -4 is on the right. If we look at a number line, or if you want to think temperatures and whatnot, -4 is pretty much not fun, but it's better than -5. For this, the 0.7 really doesn't do anything. It's the 3 compared to the 2. When decimals get involved, we just have to look to their places to make our comparisons. So generally speaking, 3s beat 2s, but in -10, no, 2s beat 3s. -2 is better than -3. Decimals here, again, just focus on the places, don't worry about the decimals. Neither one had a whole number, and then 3 is compared to 2. Normally 3 beats 2, but not with negatives, and negatives 2 beats 3. This one involves the least thought of all of them so far. Anytime a positive is compared to a negative, positive is a guaranteed winner. Okay? All the positive numbers are on the right of the number line. All the negative numbers are on the left of the number line. When a positive compares to a negative, it always wins. If a positive compared to 0, it always would win. Positives beat the other types of numbers. Negatives, similarly, this is not a lot of thought in this comparison either. Just like positives always win against the other types, negatives always lose against the other types. 0 would always beat a negative. Positives would always beat a negative. Negatives can't beat anything other than a sum of the other negatives. So if you have 2 negatives, you have to think a little bit about it. But if you have a negative versus any other type, no thought involved. Negatives always lose. Positives always win. 0 can win or lose because it's right there in the middle. Where we are, homework off of these groups, there's not a set of either of these. Neither of these is that giant of an idea to force a whole set of stuff. So the triangles will take us 205 to some letters, A to C. And then the comparing is going to take us to 207, and we're just going to do all of 207. 207 has some letters that focus on the comparing, and then it has a 1 to 25 that does the usual blend of everything we've ever seen.